Hello. I'm very pleased to open this 12th edition of the Conference of Integrability, Engagement, String Theory, and I'm proud to notice that I was present on all 11 previous conferences. My talk will be about new integrable planar quantum field theories in 3 and 4 dimensions from strongly twisted n equals 4 super Young-Mills theory, mostly based on collaborations with Joao Caetano and Omer Gurdogan, the postdocs from École Normale. So it's needless to say in this audience that planar n equals 4 super Young-Mills and 3-dimensional ABJM model are all loop integrable. It is a well-checked but never proven statement, never rigorously proven statement. We have only many calculations which are in the favor of this statement. Then the next thing to say is that they admit various integrable deformations. So at the end, I got this joystick, which is very difficult to play with. Then here we propose a new chiral field theory. We'll denote it as QFT in specific double scaling limit of gamma deformed n equals 4 super Young-Mills, namely large imaginary gamma twists at weak coupling and weak coupling. Sorry, I would prefer to change for this thing. Yes, but how to make it working? Okay. So just to immediately make a striking point, this action, which looks very simple, the two-scalar action, the action of two complex scalars phi1 and phi2, interacting through this single phi4 vertex. This theory is integrable in planar limit as in the same sense as n equals 4 super Young-Mills. It happens that it has a limited set of Feynman graphs for each correlator. One can say roughly that it's one graph per loop order for each physical quantity. And typical graphs are of fishnet type, square lattices of massless propagators, which actually shown to be explicitly integrable by Alexander Zamolodchikov in 1980. So these graphs define a non-complex spin chain which can be solved, which is integrable. And this fact explicitly reveals, without appealing to string duality, explicitly reveals in the Young-Mills theory the integrability at any coupling or at any loop order, if you want. Integrability, in particular asymptotic beta ansatz or quantum spectral curve, can be efficient tools for calculating these correlators, anomalous dimensions, structure constants, but also we claim that it could be an efficient tool for computing multi-loop Feynman graphs for, say, for scalar phi4 theory, already with epsilon regularization, for example, and we will explore this possibility, exemplify on a couple of types of graphs, which we call wheel graphs and multi-spiral or spiderweb graphs. Okay. This was the introduction. Now I start from explaining what is gamma twisted n equals 4, super young Mills. First we start from untwisted one, familiar one, to see how it will be twisted. Here is the action, which the interaction terms contain typical phi4 or Yukawa interactions. And now we notice that various fields are charged with respect to R symmetry, and the charges are given here, the table of charges. Gamma twist corresponds to the fact that you substitute various commutators. You can represent this action, as we know very well, in terms of commutators. And we substitute commutators to Q commutators, namely they will be the terms will be decorated by these factors Q and 1 over Q, depending on charges of the fields, as was prescribed in these papers. This factor looks as follows. We have here three parameters, gamma 1, gamma 2, gamma 3, corresponding to, and these parameters now appear in the twisted action, gamma twisted action here. You see various gammas appearing here, then gamma plus minus are defined here. And of course, gamma deformation breaks all supersymmetry and R symmetry up to 3 U1 groups, hopefully preserving, at least classically preserving, the conformal symmetry, 4-dimensional conformal symmetry, but we'll see that there are some anomalies here. Okay, so this is an old stuff. Now we go to our double scaling limit of strong imaginary twists gamma and weak coupling. G goes to 0, the Young-Mills coupling. Here it is, so G goes to 0. The twist factor goes to infinity, which means that gammas go to imaginary infinity, and we keep the factors xi j, these products, fixed for all three parameters. So what happens with the theory? Some terms have, like commutators, negative powers of this twist parameter, some positive. So those who have negative disappear. The gauge fields disappear because we have extremely weak coupling. So it's non-gauge theory, and here is how it looks like. You have, apart from Gaussian part of the action, you have interactions which contain retain some of the phi4 interactions listed here, and some Yukawa terms, but some of them disappear, and we will see what are the consequences. In particular, a drawback of this theory is that the action is not unitary because the gamma twist is complex. So we study essentially this theory, but we can do the same trick in the gamma twisted ABJM model. We can also go to the double scaling limit. There is actually, it boils down to a single twist, gamma 3. So K goes to infinity. It's weakly coupled gauge field, which disappears, and the double scaled coupling psi is kept fixed. Then what do we get instead of the well-known ABJM action? So we get interactions of 4 scalars with we get 4 scalars and 8 fermions, and the interaction contains, first of all, Yukawa type terms, which of course are of the type psi bar psi y bar y in 3 dimensions for dimensionless and the scalar action contains only these terms, which actually later will give us the typical graphs of the theory are the regular triangular lattices. The gauge fields and some scalar Yukawa interactions are decoupled in this limit. Okay, now we study most of the rest of the talk. We will study a special case which we find especially curious. This is this theory which I presented in the introduction. So in the full double scale theory, chiral field theory, we have put 2 couplings to 0, and we retained only the 3rd coupling, which we call psi from now on, and it leaves us with this bi-Scalar theory, as we call it, with a single interaction term. So now I present the perturbation theory in terms of double-lined Feynman graphs, as we should do in the large n limit. So the propagators are of 2 types: of phi1 propagator, which is drawn by solid lines, phi2 propagator by dotted lines. All of them, of course, are standard massless propagators in 4 dimensions. And we have the only vertex, and we notice that this vertex is sort of chiral. It's when you go from field phi2 to field from field phi1 to field phi2 clockwise, the order is fixed of these fields in the vertex, and the second vertex, which would be the Hermitian conjugate, is missing. That's the rules of the game here. In principle, we can recover this vertex, this second vertex, in the opposite limit of very small twist, and here the xi's, which are ratios, are fixed. So the second chirality will emerge, but the first one will decouple completely. When I speak about chirality, we rather should define it on the planar graphs than in 4-dimensional field theory. So like we do in string theory, for example, defining the chirality of fields. Okay, so this vertex is excluded in our limit, in the first limit. And actually, with this single vertex, we have very limited number of planar graphs. As I said, at most 1 graph at each loop order. A similar 0-dimensional theory was considered by completely different, from completely different point of view by Ivan Kostov and Matthias Staudacher long ago, where they noticed very limited number of graphs. Here it emerges in our context from n equals 4 super young gamma twisted n equals 4 super young mills. Okay, so let's apply now these Feynman rules to analyze the properties of this theory. As example, we will see that there are no mass or vertex renormalizations in planar limit by simple topological reasons. If you draw the corresponding graph, which would renormalize our psi coupling, you simply notice that it should consist of one vertex with correct chirality, whereas the other vertex is absent by the reasons explained above. So this is excluded, and one can see higher loop graphs, they will have the same property. So the psi coupling is not renormalized in the planar limit, of course. Now, if we do the same with the mass renormalization, we will notice the same. One vertex is chiral, another anti-chiral, so it's excluded. But we can always draw this kind of graphs, which many people noticed in various occasions, and in particular in the papers of Zieg, Fokken, and Wilhelm. They investigated this instability in gamma-twisted tentacles for young males and noticed that the theory cannot be conformal in the usual way, even in the large n limit, but there are special properties of this theory. So here I list another possible counter term which generates this kind of double trace vertex. So we can generate only double trace vertices, and in principle we could calculate the corresponding beta functions, as was done by Zieg and Wilhelm. And it seems that we cannot apply our rules of the game, namely the theory is not conformal, what will we calculate? But fortunately, in spite of the fact that these double trace couplings are running even in the planar limit, the Xi coupling is not running in the planar limit. So we can, and there are many correlators, many correlators, which show perfectly conformal behavior in the large n limit. Essentially, we should avoid appearing in the initial states or in internal states of these correlators, the states which are of the length 2, this kind of states, trace phi phi or trace phi dagger phi. So we can study the theory for this kind of correlators, conformal correlators. We can study the theory at 0 eta couplings. That's our strategy. Beta functions for etas were computed by Zieg and Wilhelm recently. There was an interesting, the existence of an interesting fixed point was advocated for finite etas. That's something which deserves study, further study. Okay, then one comment that if we try to compute 1 over n square corrections to, for example, to this correlator, I should have shown it later, then we will realize that this, since we have to distribute the lines here of phi 1 field from the south pole to the north pole in all possible fractions, sometimes it will be 2 lines passing here, and the state length 2 will pass through one of the half periods of this torus, and it will collapse anyway. So it looks typically tachyonic, as a typically tachyonic situation. The states of length 2 play the role of tachyons. It was already noticed in gamma-twisted dual string theory, and that strong coupling, it was pointed out by Pomoni and Rastelli. So we deal with tachyonic states. Somehow these considerations are carried over to the pure field theory, this bi-Scalar field theory. It's an interesting question whether we have a string dual for our field theory, not guaranteed since we work in the extremely weak coupling limit where the sphere and the ADS are supposed to collapse, but who knows, maybe some new string theory emerges in this limit, which is already 4 or 5 dimensional, not 10 dimensional. We can also try to combine chiral and antichiral Walsh fields in this, at each order of expansion in this string field theory. Who knows, maybe this could give a nice definition of strings in less than 10 dimension. Now let's study particular states. So local operators can be formulated as the mixture of phi 1s, phi 2s, and phi 1 dagger, phi 2 dagger. In principle, we also can have the derivatives. So there are many more operators here. all kinds of derivatives intertwined, but we will study today only these operators. And in particular, it is known that, that for BMN vacuum in the gamma-twisted super young Mills, the correlators of two BMN vacua are non-trivial. They develop the anomalous dimension due to the wrapping effects. And here, it's in this bi-Scalar theory, we can see it really explicitly. When we start drawing the graphs for this two-point function, so the only graph which emerges is of this type. So you have phi1 fields going from the North Pole to the South Pole, from 0 to x. And the fields phi2 can emerge only as circles interacting in this chiral vertex, this only chiral vertex, so they have to be directed in the same direction. So you can draw any number of circles here. We call it sometimes a globe graph. So you cannot draw any other graph in this theory in the planar limit for this operator. So we see already that there is very limited number of possible graphs here. Now, when we study the anomalous dimension, when we calculate anomalous dimension, we can concentrate on the, for example, south pole of the sphere and amputate the, since the ultraviolet divergences should be concentrated around one of the poles, and amputate all the propagators which go to X, L propagators, which give trivial bare contribution to the dimension to L. Okay. Then the resulting graph, which emerges here, is the standard scalar graph of scalar field theory. You forget about how that some fields were phi1, phi2. So you simply calculate at each order, at each wrapping, this kind of graph with any number of frames here in this wheel. And L is the number of spokes in this wheel. So it's already clear that if the theory is integrable, it can give us access to very complicated multi-loop Feynman graphs of simple scalar field theory. And what is important to individual graph, because graphs in n equals 4 young Mills, before this limit, you sum up many graphs, yes? So you can study invariant, scheme invariant combinations of graphs. Here we really can study graph by graph this theory for individual graphs. So the anomalous dimension can be written as follows, where the single wheel contribution was computed long ago, these kind of graphs by Broadhurst, and was used by Fock and Wilhelm for computations in gamma deformed super young Mills, from where it can be also extracted. And the second coefficient is much more complicated. For example, I should also mention that this result that should be shown later. Okay, sorry. So for I only wanted to say that for the double wheel, the results are much more complicated. For length 3, it was computed directly as a Feynman graph, and it will coincide with the result of integrability calculation. This is the result of from our paper with Omer Gerdogan for length 4. This one, of course, appeared in the paper, due to which we know these contributions. Actually, this was a beautiful paper of Anne Beinok, Bombardelli, Nepomici, really coup de force, who calculated this correction in terms of double integrals and infinite double sums. So we worked hard to transform their not very explicit result into explicit MZV form, multiple zeta values form. So there is an explicit expression in terms of finite sums up to L of all these MZV. And these are particular cases for this wheel. So we can compute, of course, these are so-called periods of these graphs. The coefficient in front of 1 over epsilon in epsilon regularization. So it's obvious that even the structure suggests that the theory should be integrable. Okay, now let me discuss the integrability already, the explicit appearance of integrability in this model, at least for these wheel graphs. So the Hamiltonian generating wheel graphs can be presented here. So it's a chain, periodic chain, where these propagators are given by inverse Laplacians with respect to each four-dimensional variable here, x1, x2, etc., xl. So we move from here to here, from here to here, etc. We move using this operator, and then we add these propagators explicitly, the product of nearest neighbors here, and each time we act by this H, we add the wrapping order psi to the 2L. So then if we continue this, if we take a square of this operator or a cube, we will grow our wheel graph. Then we have to identify here the ansatz 0, which is quite a complicated state, of course, when you put all these coordinates to 0 here. Fix the four-dimensional coordinates at zeros. So we have to diagonalize this Hamiltonian, or at least to observe its integrability to begin with. And actually, the conformal symmetry can be easily checked. If you transform, if you do the only non-trivial transformation of inversion, the Hamiltonian transforms covariantly in this way. Also you can construct the transfer matrix out of Lax operators in principal series representation in quantum space and fundamental representation in auxiliary space using gamma matrices, etc. So you can explicitly check this commutativity. We checked it on Mathematica at the length, the first non-trivial length equal to 3, where you have the first non-trivial conservation law in transfer matrix. But now it's obvious for us due to the explicit construction of R matrix in principal series versus principal series, from where you can even extract the Hamiltonian explicitly for particular value of spectral parameter using the formalism developed by Checherin, Derkachov, Isaev. It goes about our work in progress with Stefano Negro and Gregory Korchemsky. Okay, now, so in this sense, the integrability of bi-Scalar model, at least for this state, is demonstrated explicitly in all orders, which is the first time that directly from quantum field theory, on quantum field theory side, you see explicit, you can prove the integrability. Now, another way to see this integrability is to go back to the Zamolodchikov's paper, old paper. Maybe I should point out that when you construct arbitrary big graph of this kind, locally it is a regular triangular lattice, only with a defect here and with some boundary. But the bulk of it is, as you clearly see, just regular square lattice. And that's precisely what Zamolodchikov's, that's precisely the integrability of this graph that Zamolodchikov observed long ago. And the story goes as follows. standard in statistical mechanics of Baxter type models. So you define Baxter lattice of really intersecting lines. You dash even faces of this lattice, leaving blank white faces in the obvious manner, as you see here. Everything is characterized by a set of lines, by the set of angles between lines, which are kept fixed. Then you put in the middle of each white face a four-dimensional, or a d-dimensional variable, actually. This works in d dimensions. A d-dimensional variable x with the label j, say 2 here, and connected by propagators, the powers of nearest neighbors which depend on the angle. Say this propagator depends on this angle, adjacent angle. And then you multiply all propagators and integrate in d dimensions the whole configuration. This is sort of a disordered Feynman graph. And to show its integrability, one should simply show that one can take, for example, one of the lines and move it freely through the intersections up to some scalar factors. Namely, you have to consider this configuration, and you have to show that, for example, if you have this integral here, so if you move this line, you get this configuration with white triangle instead of black. So if you integrate out here, you get simply the product of this. You restore the whole form of these integrals as product of triangles here, which is simply the famous star triangle relation known known to many people even without integrability. But here it appears as a form of Young-Baxter relation. Now, if we we can slowly straighten, slowly make one sequence of lines parallel and vertical, another sequence, another half of the lines parallel and horizontal, and when we do it carefully using various limiting relations of various limits of this star triangle relation, we come to the integrable regular square lattice with propagator. In 4 dimensions, the propagators will be precisely of massless scalar type. So this proves that the corresponding graph, at least the bulk of it, is integrable. But we have many various boundary conditions for this graph for various operators. Now that I already said that there exists a non-compact integrable superconformal quantum spin chain which solves this model. And I also mentioned that if you choose 3 sets of lines which intersect by these angles, so you get so-called Kagomel lattice, and if you put the vertices into white faces, you get triangular lattice with this propagator, which is typically in 3 dimensions, which is typical 3-dimensional massless propagator. And this is the typical graph for ABJM model, of which I will not speak much about, but we are preparing the corresponding results in our paper with Omer and Joao. And also, curiously, if you place vertices in the dashed triangles, you get the hexagonal lattice with massless propagator. Of course, this is phi cube interaction, which is dimensionless in 6 dimensions, and who knows, maybe I know little about little string theory or these 6-dimensional gauge theories, but maybe one can twist them to get this kind of typical graphs and integrability in addition in a certain limit. Okay, so this is the review of Zamolodchikov. application of the logic of fishnet integrability to our typical graphs of bi-Scalar theory. Now I discuss slightly more complicated operators, namely with inclusion of magnons, where the life is even more diverse. So we now have a few magnons, insertions of phi2 field on the background of phi1s. For example, here and there we have two magnons here, phi2 magnons, and we study the anomalous dimensions of this operator. Of course, we should, if we don't know anything about integrability, we should compute Feynman graphs. And the Feynman graphs are sort of not generalization, but slightly different from globe graphs. They are built of multi-spiral lines, double lines, triple multi-spiral line winding around a few meridians made of propagators of phi1 field. And notice that it still looks as fishnet in the bulk. If you draw many, many such spirals, you will get in the bulk up to boundary conditions somewhere in the ends, you will get the fishnet type graph, integrable again. So you see that this red line of phi2 propagator starts somewhere from the North Pole, goes around the globe and ends up here. The second one also does a similar thing, sort of in parallel. Let's give the examples of one magnon graph. For example, this is one magnon graph before wrappings. It goes in such a way that none of the phi1 propagators is crossed twice. So this, as you suspect, could be a subject of asymptotic beta Ansatz study. Then if we amputate the propagators going to one, for example, to North Pole, the resulting graph looks as follows. Yes, it's sort of a spiral which starts here and ends up there. All these legs are amputated. The ultraviolet behavior can be studied well only by this graph, not the whole one. Then with wrapping, you see, for example, the spiral intersects twice this set of propagators, this phi1 line, and the corresponding graph also, the corresponding amputated graph shows the same feature. This link is intersected twice. And these are single graphs every time. If you take one monomial out of, if you compute the correlator of two monomials, not with all permutation, but two monomials, you always end up with one single graph here, which is nice, and it's a graph of scalar theory. Now, if you make many wrappings, for example, with a single magnon graph, it looks like a spider net. So maybe spiderweb. So maybe these graphs should be called spiderweb graphs. Okay, this is a zoo of the graphs we study with these magnon operators. And now, as I said, it's natural to apply to at least unwrapped graphs the asymptotic beta Ansatz, the well-known tool of integrability in n equals 4 super young Mills, now applied. So we have to find the limiting double-scaled limit solutions of the corresponding ABA equations. What we have done, but not yet published, with Omer and Joao. I recall that the magnons are characterized by rapidities U1, U2, etc., up to the number of magnons in ABA. And the equation which we got, it shows that the only way to find the solution is to go to mirror plane in this equation. That's why we get this kind of interaction. Then it's weak coupling. That way, at the end, we get something directional, but not unitary beta Ansatz equation. It's natural to have to work in the mirror plane, because once the magnon gets out of the vertex, it starts going, winding around this globe, which is the direction of mirror particle usually, for those who remember what it is in asymptotic Bethe ansatz. So it's very natural to look for solutions here. And after careful scaling of all these parameters, we found psi, our only coupling, entering here explicitly. And the dressing phase is mirror-mirror, and it has this rational form. So we have here perfect scaling, and we also managed to find this scaling in the case when you have all three scalars for the full theory, all phis and psis in the full double scale theory, but not phi bars and psi bars, for example. Then we didn't yet manage to find the full asymptotic Bethe ansatz for all states, including derivatives. Some more work is needed. Okay. For example, we can use it to compute the anomalous dimension of one magnon state. And naturally, you get the solution of this equation. Then you reproduce the dimension with only one exponent of this cosine square p over 2, which is equal to the twist variable, like this. So that way you get the solution for one magnon, which is, of course, simply read off from the well-known result of these papers. And this already here, what one should stress, reproduces the graphs of this type. So this is all these propagators are at 0, these are at x. You compute the amputated propagators of this type, and they're equal to Catalan numbers, a very well-known result. But it's just a demonstration. Now, if we go to two magnons, a more interesting case, we reproduce the dimension from this asymptotic Bethe ansatz, and we know that this dimension corresponds to the following mixing matrix. What is nice in this chiral field theory that each term of this mixing matrix is actually a single graph, which is equivalent to a single index structure with respect to the indices of phi 1 and phi 2 fields. So they are all listed here. This is the full for-loop dilatation operator. So computing the entries, we compute single graphs, which of course is a trivial statement here. And we can do it from integrability and fix all the structures here up to one single constant at 4 loops. Say at 5 loops it will be 2 constants. It was analyzed, I guess, by Nicholas and co-authors in the full Young-Mills theory, how the uncertainty, in particular coefficients of dilatation operator, increases with the order. Here we have to fix. So the point is that if we fix this constant c in one particular favorite renormalization scheme, we calculate all these scalar graphs. And then as an example, for example, we can explicitly compute, even by computer programs, which Omer is a big specialist in, we can compute this graph, which we call simply connected graph, like it has only one vertex connecting two parts here. This is the result in epsilon regularization. But then we can simply compute the corresponding coupling using this result from the previous transparency. It is equal to that in epsilon regularization, and it completely fixes the other slightly more complicated graphs, which are nevertheless known. 2 minutes. So the message is that the integrability in chiral field theory can be a powerful tool for computing complicated Feynman graphs. And I maybe only flash with the transparency for computation of a wrapped single magnon graph, which we can do in epsilon regularization, so with all terms of epsilon regularization, which we can do knowing the wrapping correction to anomalous dimension computed in these works by integrability or by direct graph computations. And also the unwrapped graphs of higher length, which of course, all the contributions to these graphs are very similar. So this was computed by Gross et al., Gross, Mikhailov, Reuben. Then we can go to through the standard renormalization procedure and notice that up to L-1 loops, both graphs have the same Bayer propagators because the wrapping is not yet felt, the same 1 over epsilon extensions of each of these integrals, Feynman integrals. Then we actually notice that only 1 over epsilon term is different in two cases, which can be fixed by the knowledge of delta gamma wrapped by going through the standard procedure of computing the renormalization factor, renormalizing the Bayer propagator, etc. Okay, here are a couple of results for length 4 and 5, but Joao has a program which generates any reasonable L here, 1 over epsilon term. The rest of terms are known. Okay, that's our conclusions. So it's here it's clear that we found the theories and the double scaling of two interesting theories. That integrability of quantum field theory is related to fishnet graphs. And this is the first explicit demonstration of all loop planar integrability of n equals 4 super Young mills, at least in this corner of phase space. Okay, that I mentioned. But maybe what can we... so it could be a powerful tool of computing individual graphs, in particular regularizations. Now many other quantities probably could be approached by integrability methods, and they are much easier computable than n equals 4. The question, what is dual string theory to these theories? And we should actually study and scale out the quantum spectral curve equations. It is in the process to build this particular limit of them. And the inspiring results were obtained by Gromov, Levkovich, Masluk with a similar limit of in the quark anti-quark potential, which is a bit simpler because you sum ladder graphs in this case. So thank you very much. Yes, the dilatation operator, yes.
How is that possible?
In these theories, it's possible because each entry of this operator is defined by a single graph. Then we have one-to-one correspondence, except some parameters which which are scheme dependent and which have to be fixed from computing the simplest possible graphs, and the rest of the graphs will be defined by integrability.
You mentioned that in principle there would be double trace operators which would perform that action. But so the understand correctly is that what you have proved is that integrability is there for a particular class of operators. If you start to compute correlation functions for generic operators, and double trace somehow should also be taken into account, or this is not the case?
No. Once, if you want to compute for example, the 2-point functions of operators of length more than 2, you don't need these couplings. If you put them to 0, they simply, it's a magic of large n, they simply will not appear in the perturbation theory. You can show explicitly that only in 1 over n square expansion they can appear. And Yeah, but for example, you can approach by these methods maybe computing non-perturbatively the beta functions of eta couplings for small etas in all orders in Xi. This is an interesting project as well, to study the scale dependence of the theory using integrability methods. But it's probably as complicated as computing one-point functions or three-point functions, but not impossible. Actually, I have to thank Benjamin Bassot and Kostya Zarembo, who explained me a lot about various aspects, about various questions which I raised in this talk.
I have a question about the emergence of SY2 symmetry in this method. Perhaps I'm misunderstanding something, but this should not be related to the conformal symmetry of the space-time, because as shown by Vladimir Kazakov, if contains higher spin charges, there's a greater massive free.
Sorry, I didn't hear well.
If a theory has higher spin for subcharges,
Yes.
the greater the theory must be free.
Yes.
But now you mentioned there is some emergence SY2, spin chaining.
Yes.
What is the relation between?
No, but the theory is it's still about conformal symmetry. You have, if I answer correctly your question, you have operators which don't contain derivatives, but they could. There is a larger class of operators which transform with respect to this conformal group. But even for these operators, you can have intermediate states which are operators with derivatives. So you have full-fledged four-dimensional conformal symmetry which acts in this model and corresponding states as well. So the spin chain should reflect it. For example, if you build this, if you consider this graph building Hamiltonian, which I mentioned, it acts in the space of four-dimensional variables, and it's conformal operator. So, of course, the conformal group is omnipresent in all calculations, and the spin chain should be conformal. But in principal series representation.